Welcome to the presentation. I'm Faisal, and today I'll be talking about analog and digital electronics. Let's start with the introduction. Importance of analog and digital electronics. Analog electronics. Analog signals have a lower bandwidth requirement than digital signals. Changes in physical phenomena such as sound, light, temperature, position, or pressure are better represented by analog signals. Electrical tolerance is less sensitive in analog communication systems. Digital electronics. In today's environment, digital electronics is incredibly important because, unlike analog circuits, digital circuits allow signals to be transmitted without degradation due to noise. Applications of analog and digital electronics. Analog, measuring equipment, sensors, amplifiers, filters. Digital, electronic devices include cell phones, calculators and personal computers, radios and other communication devices. A signal generator is a device that generates signals. The intelligent card, cathode ray oscilloscope, analog to digital converters, digital to analog converters, and so on. Usefulness of analog and digital electronics. Analog electronics has an elegant design with many components, and it would provide the digital world a tremendous boost. If analog techniques, processes, and subsystems were not utilized, modern digital systems would be underpowered, input only and output only. Analog communication technologies are less sensitive in terms of electrical tolerance. Computers, information appliances, digital cameras, digital televisions, flash memory, USB key memory, mobile phones, and disks, and computer memory devices all employ digital signals. After analog signals have been transformed to digital form, digital signal processing is used. Electronics analog and digital signals, which are usually electric signals, are used to transmit data. Each of these technologies converts information such as audio or video into electric impulses. Thevenin's theorem and superposition. Thevenin's theorem. In the development of electrical and electronic circuits, for example, according to Thevenin's theorem, any linear active network with independent or dependent voltage and current sources and network pieces can be replaced by an equivalent circuit with a voltage source in series with a resistance. Explanation. Any linear circuit, no matter how complicated, can be reduced to an equivalent circuit with a single voltage source and a series resistance according to Thevenin's theorem. Example, to find VTH, RTH and the load current flowing through and load voltage across the load register in the circuit below using Thevenin's theorem. First, remove the 3 kilo ohm from the circuit by measuring open circuit voltage to get Thevenin's voltage means VTH. So I is 3 mA. The voltage across the register is 6V, and the Thevenin's voltage VTH is 6V. Then calculate the Thevenin's register or equivalent register. RTH is 5.5 kilo ohm. Now find out load current and load voltage by Ohm's law. Load current is 0.705 mA. Load voltage is 2.115 V. Thevenin's theorem in practice. Thevenin's theorem is utilized in power system analysis, source modeling, and resistance measurement utilizing the Wheatstone bridge. Limitations of Thevenin's theorem. Thevenin's theorem is only used in the analysis of linear circuits. The power dissipation of the Thevenin equivalent is not the same as the real system's power dissipation. Superposition theorem. the assumption of linearity between the response and excitation of an electrical circuit underpins the superposition theorem. It asserts that when numerous independent sources act at the same time in a linear circuit, the response in that branch is equal to the total of the responses owing to each independent source acting at a time. Only one independent source will be considered at a time in this procedure. As a result, the remaining independent sources must be removed from the circuit. The voltage sources can be eliminated by shorting their two terminals, and the current sources can be eliminated by opening their two terminals. Find V in the circuit using the superposition theorem. Let V is V1 plus V2. First, remove the 1A from the circuit. Now calculate the current flowing like I1 by using Kirchhoff's voltage law. So I1 is 0.5A, V1 is 1V. Now remove 3V from the circuit. Find V2 by using current division. So I3 is 0.66A, V2 is 1.32V. Then to find out V is V1 plus V2 is 2.32V. Theorem of superposition's limitations. Nonlinear circuits are not covered by the theorem because linearity is required. The superposition theorem can only be used to calculate voltage and current, but not power. When only one source is considered at a time, power dissipation is a nonlinear function that does not add up to an accurately total algebraically. The superposition theorem necessitates the presence of two or more sources in the circuit. Multiplexer. A multiplexer has at least two N data inputs, N selection lines, and a single output line. One of these data inputs will be connected to the output based on the values of the selection lines. Because there are N selection lines, there will be two N possible combinations of zeros and ones. As a result, just one data input will be selected for each combination. Multiplexer is sometimes known as MUX. A 4x1 multiplexer is a device that combines four channels into one. It has four data inputs, I3, I2, I1, and I0, two selection lines, S1 and S0, and one output Y. The block diagram of a 4x1 multiplexer is shown in the diagram below. One of these four inputs will be connected to the output depending on the combination of inputs or at these two selection lines. A truth table for a 4x1 multiplexer is shown below. The output Boolean function y may be written as y is equal to s1 prime s0 prime I0 plus s1 prime s0 I1 plus s1 s0 prime I2 plus s1 s0 I3. Inverters, AND gates, and OR gates can all be used to create this Boolean function. The diagram below shows the circuit schematic for a 4x1 multiplexer. We can easily understand the operation of the above circuit. Similarly, you can implement 8x1 multiplexer and 16x1 multiplexer by following the same procedure. Ring counters. The last flip output flop is connected to the first flip input in a ring counter, which is a shift register, a cascade of flip-flops. Flops, the remainder is set to 0 and just one of the flip-flop outputs is set to 1. The 1 bit is calculated when n flip-flops are used and the state repeats every n clock cycles. The modulus of a counter is the number of distinct states. The mod of the n flip-flop ring counter is n. It can be implemented with D-type flip-flops or JK-type flip-flops. To enable the flip-flops, press the reset blue button. A toggle switch, the reset switch, allows to turn something on or off, like a room light switch. By pressing the clock black switch, you may examine the outputs of the flip-flops. The clock switch is a momentary switch, like a doorbell switch normally off. The D flip-flop clock's input is rising edge. Q1, for example, behaves as follows. The D input value immediately before the clock rising edge is worth noticing. When the clock rises, the D value previously specified is applied to Q1. The mod number of unique states of these 3 flip-flop ring counters is 3. Conclusion: a blend of analog and digital components is likely to be used in the future of analog electronics. Analog electronics has a very elegant design with a lot of components, and it would give the digital world a huge push. Here are all the references. Thank you so much.